finished today for sure. And what I just did before class, I created a correction. I was trying to figure out the easiest way to have you do corrections on them if you didn't get full credit. And so what I did was just created another page underneath the worksheet. So you should see this page in your account now. If I just go to a random account now and look under Chapter 6, there the corrections will be. So you'll see that now, and what I want you to do, I'll give you 2 weeks. I'll get them finished grading today, and if you get full credit on it, then nothing for you to do. But if you just got partial credit on it, it'll say out of 5 points. You know, it'll say 5 out of 5, 3 out of 5. You could have got a couple of minor things wrong, and I'd still give you 5 out of 5. But if you didn't get 5 out of 5, you'll have 2 weeks to just insert the ones that you didn't get full credit on. And then I will bump your thing up to full credit. If you just blew it off and got 0, you can still do the same thing, except you can only get up to 4 points. If you did nothing, you can do it for partial credit. You can do it for 4 points. And it'll be due in 2 weeks. 2 weeks from Monday. 2 weeks from Monday. So I'll get those all out to you today. So you'll see them later today. And you'll see just a grade right at the top. Yeah, I'm not going to pick on anyone right now, but any questions on that? Pretty simple, straightforward. If you have questions, of course, ask. Let's go over to our integration stuff because we're doing we started this already, good. We are doing some very cool integration right now. We are learning really your second technical integration technique. 8.1 is just filled with a bunch of one-off kind of integration techniques. It's like, if it's an improper fraction, divide. If you have negative exponents, get rid of them. Just kind of strategies, but not formal integration techniques. So this is our second integration technique. We've got U substitution, and now integration by parts is kind of a U substitution on steroids that we can integrate a whole bunch of cool things with. So let's just do some examples. And remember that we are going to separate the integrand into U and dv. So we're always going to make this little table here, and the dx always has to go with the dv. And we have to sort of take our integrand and pick what goes where. And when I look at this, I see 2 functions. Let's do it this way. So I see the x squared function and I see the natural log function. The dx has to go with the dv, so there's no choice there. So we really have 2 choices. We could put x squared here and natural log here. We could put natural log here and x squared there. We have 2 choices. And the one rule of thumb that I want to emphasize, integration is always harder than differentiation. Whatever you put there, you can take the derivative. You know how to take the derivative of anything. But what you put there, you have to be careful because it has to be integrable. So when we look at these 2 functions, x squared and natural log of x, let's just ask ourselves, is x squared integrable? Yeah, of course, x cubed over 3. That's a pretty straightforward integral. What about natural log of x? Do we know how to integrate natural log of x? You certainly know how to differentiate it, right? The derivative of natural log of x is 1 over x. We know that. But do we know the integral of natural log of x yet? No. You know how to differentiate it, but you don't know how to integrate it. And that sort of tells us what we need to do then. That tells us that, put the natural log here because you know how to differentiate it. And let's put the x squared over here. So that is the focal point of setting up your little integration by parts table here. You want to put the thing you know how to integrate right there, and if there's part of it that you don't know how to integrate, of course it has to go with the derivative column. It can't go in the integral column. Now, if it doesn't matter, if both things are integrable, then usually what you want to do is put the the biggest chunk of it that you can integrate right there, if both are integrable. All right, so let's go for it. So the derivative of natural log of x is 1 over x dx. The integral of dv is v, so we integrate both sides here. And one of the nice things about integration by parts with this column here, when we do integration, we don't need to do a plus c. We can choose the plus c to be 0 every time, and it works. If you want to be a contrarian, you can pick a constant that's not 0. If you want to pick 7, you can put it there, and it will work. I'll pick 0. So then we do our ultraviolet voodoo. So our integral is equal to uv. So this is ultraviolet. This is the main diagonal right here. And I'm going to call that the main diagonal. As you go on, some of you have already had matrices, some of you haven't. When you're dealing with a matrix is an array of numbers, they will always call this diagonal from top left to bottom right the main diagonal. And you'll learn something called the determinant, where you take the main diagonal's product and you subtract off the other diagonal's product. But that's why I'll call it main diagonal, because when you get to matrices, they look kind of like this. That's going to be your main diagonal. Yeah? I can write down the ultraviolet voodoo thing.
And can you go through how it works with this equation?
And say that again?
Can you go through what parts of that works with this equation?
Yeah, so the first thing with integration by parts is we usually think of it as a reverse product rule. So if we see a product of functions in the integrand, that integration by parts should be a candidate for the integration technique if you see a product of functions. We'll see other techniques too for products, but that's the main thing. So when we look here, we see a product, and our goal then is to separate the integral, the integrand, into u and dv. So we take our integrand, break it apart into u and dv, and then that's the integration. So the integration, so we separate it, we put the natural log here, we put the x squared there, so now we have the u and the dv. Now we're going to form uv, which is the main diagonal. So that'll be 1/3 x cubed natural log of x, main diagonal. And then we subtract off the bottom row. So uv, ultraviolet, minus integral of voodoo, v du. So then this will be the test point. When we look at this integral here, if this integral is easy, great. We're doing the right thing. If that integral is harder or equally as hard as this, then we have to reassess. And when we look here, we're going to have 1 over x multiplied by x cubed over 3 multiplied by dx. That's easier, right? We have a cancellation of x there. Right, well, this x will go away and make that a 2. No natural log, way easier, right? It's just the power of x. So we have a power of 2, so that's going to be x cubed divided by 3. 3 times 3 is 9. And then we add our integration constant. So that'll be our antiderivative.
What makes the very original integral hard to solve, or you can't solve without it?
So if you don't see an immediate antiderivative, if you can't use u substitution. So if you can't do what, those are the two things you immediately look at. Like if you're integrating cosine, you know the antiderivative of sine. If you're integrating x cubed, you know the antiderivative is x to the 4 over 4. So if you don't know an immediate antiderivative, then you usually think u substitution. And when you look here, if you let u be natural log of x, the derivative of natural log of x is 1 over x. There's no 1 over x here. Right? There's no u that would work. If we let u be x squared, the derivative is 2x. There's no way to get the ln x in the du part of it. So those are the two things first. Immediate antiderivative, u sub. If those don't work and you have a product, then think about integration by parts. Ultraviolet voodoo. Now, yeah?
Will this always work, or are there cases where ultraviolet voodoo?
Oh, we will see some cases where it works in a slightly modified way. We'll call it ultraviolet voodoo with a twist. And there will be some where doing integration by parts just doesn't make sense. Like there's some that it won't work for well.
So could you apply this method to like all the problems that we're doing in Python?
That's a good question. Bless you. I don't know. I've never tried. So your question was, can we apply this to the other, instead of using other techniques, could we use this? And I don't even know if this, I don't know if it's true that you could use integration by parts every time that you use usub and have it work. It might be true. Yeah, we should try that. That's a great question. Huh. Because if usub works, usub is just faster and easier, so most people wouldn't apply integration by parts. But that doesn't mean to say it wouldn't work. Yeah, well, let's keep that in mind as we go. Now, in general, we're thinking of it as a reverse product rule. So here we had a product, x times 1 over square root of x plus 1. Here we have a product. But what's really fascinating about integration by parts is that you can integrate a whole bunch of functions that aren't really products, but are functions that you have no clue how to integrate yet. We don't know how to integrate inverse trig functions. We know how to differentiate them, but we don't know how to integrate them. Natural log, super common function, super easy to take a derivative of, 1 over x. But we've never even talked about the integral of it. Well, integration by parts will allow us to find the antiderivative for that. So let's check this out. So again, we set up our table same way every time. So we're going to make the top row the udv. And we know that the dx has to go with the dv. All right, we're going to integrate both sides here, so we need a differential on both sides. We look over here, there's only one function. It makes no sense to put it in there because we don't know how to integrate it. That's the whole point of this exercise, is to figure out how to integrate it. So we can't put it there, right? There's only one choice. The inverse sign, we know how to differentiate it. It must go right there. And this will just be a 1. You don't have to put the 1 there, but so it's the only option if we're going to use integration by parts. So we take our derivative, and we'll have du equals 1 over the square root of 1 minus x squared dx. Integrate over here, choose c to be 0. And that is our integration by parts table. That's going to lead us to our ultraviolet voodoo formula. So we're going to have the integral of v du. That will be uv minus, oh, I already have it right above it. Never mind. I don't need to write it again. It's right there. So here we go. uv, main diagonal product, x inverse sine of x, minus the integral of the bottom row, integral of v du. So v is x, du is 1 over root 1 minus x squared dx. And that integral is where, I mean, in this case, we had no choice. This is the only choice we had. But this is normally the step where you would say, OK, is this integral here something that we can manage? Is that an integrable function? Or is it worse than the original? Well, this is integrable with what technique? U sub. Because the quadratic inside the square root, if we let u be that quadratic, the derivative of a quadratic is linear, and we have a linear up top. So u sub is going to work beautifully there. So let's go ahead and do u sub. We're going to let u be what's in the square root. That's pretty common. Let u be what's in the square root, or in the exponent, or in the angle. And the numerator here we see is an x dx. So we'll isolate the x dx over here. And that will allow us to do our sub. So we have x inverse sine of x minus, all right, let's do our substitution here. So x dx, that's du over negative 2. So out in front, we'll put a division by negative 2. And then x dx is du. And the square root of u is in the denominator, so we're going to put that into the numerator as u to the negative 1/2. Whenever we have a square root or a 3/2 or whatever in the denominator, we pop it up top by changing the sign of the exponent. Then we can integrate. All right, so x inverse sine of x plus 1/2. Leave a little space. Add 1 to the exponent. Divide by the new exponent. Integration constant. We have a little cancellation. And then we just have to back substitute. The original variable is an x, so we have to get back to x. So our final answer, we will have that the antiderivative of inverse sine of x is x inverse sine of x plus the square root of 1 minus x squared plus c. So that is the antiderivative that you would never memorize. So if you take the derivative of that function, you will get inverse sine of x. That is the antiderivative. Any step there you're not sure about? All right, let's try this one. This is one that you've all been waiting for. Everyone wants to know what the antiderivative for natural log of x is. Right? It's got an easy derivative. Does it have an easy antiderivative? Finally, you're going to get your answer. Waiting for all these months. So again, we have our UDV table here. We know that dx is going to go right over here. It has to go there. This is one of these oddball integrals that just has one function, but yet integration by parts is going to work like a charm. We can't put the natural log in the dv because that's what we're trying to do here. We're trying to integrate natural log. If we put it there to get v, you'd have to integrate natural log, and we don't know what the antiderivative is. So the only choice is this. That is our only choice. So let's see what happens. Maybe it works, maybe it doesn't. Take the derivative, we get 1 over x dx. Integral side, we get v equals x. Question?
Is there ever going to be a time where you have to integrate by parts?
Oh, yes. Next slide. Next slide. There are times where you have to integrate by parts multiple times, more than twice. There's a technique called the tabular method. Oh, my son just sent me last night, he was doing one where they had to integrate by parts 4 times in a row. And this tabular method does it really fast. There's a cool little shortcut if you have to integrate by parts a ton. We won't do a ton.
How did you get v equals x?
Integrating both sides. The integral of dv is v, the integral of dx is x.
So on the left side, you just take the derivative of u and then get du, and then on that, you take the antiderivative.
Mm-hmm.
Okay.
So this column is always derivative. This column is always integral. And this tabular method that it's in, there's a couple of exercises in the homework that have it. The idea would be that you just end up differentiating a whole bunch, end up integrating a whole bunch, and there's a shortcut with that table. It's not something this book emphasizes. The old books always emphasize the tabular method. So uv, x ln x. So uv minus the integral of v du. Okay, v du.
Would that just be dx?
That'll be just dx. So these are canceling. And what's the integral of dx? X. So there is our antiderivative. X ln x minus x. That is the antiderivative of natural log of x. If you take the derivative of that function, which you should do, to make sure the derivative of this function will give you natural log of x. Let's just do it right here. So if we were going to take the derivative of this, we would do first derivative second, plus derivative first times second Derivative of negative x, negative 1. Derivative of c is 0. X over x is 1. 1 minus 1 is 0. You get ln x. Yeah, so that is our antiderivative, x ln x minus x.
Wait, question. Wait, is this just the two of them, or is it because like the last one it was the like sign, it was like inverse sign, is the x and the inverse sign plus the denominator or whatever
The coincidence.
the coincidence.
Yeah.
Yeah. Okay.
Yeah, it's not always going to work out that way.
Okay.
Yeah. Yeah, that coincidence. All right, let's try another one. When integration by parts once is just not enough. All right. So here we've got some powers of x, powers of natural log, and I can't remember if I pointed this out or not, but this is sort of a newer technique here to put the 2 on natural log. Remember that this is the first book I've ever used that does this, but that just means what you think it means, natural log of x squared. If you want to put it out there just to make sure you don't mess up a derivative, good strategy. It's very easy to mess the chain rule up with this power when it's tucked in here. It's not quite as obvious that it's 2 natural log of x to the 1 multiplied by the derivative of natural log. So that chain rule doesn't become as obvious when it's in this notation. So we'll do what we've been doing. We're going to create our integration by parts table here. We need a u and a dv. And when we look at this integrand here, this integrand, you can break the functions apart like you could do some weird things like, oh, I'm going to try to let u be x ln x, and then let dv be x ln x also. You could do weird things like that. Usually that's not going to be the move. Usually if you have an x squared, that's going to stick together. Have a natural log squared, that's going to stick together. Usually you're not going to commingle the factors and make things look really funky. So when I look at this, I'm seeing it as 2 options. We could put ln squared here. We could put ln squared there. That thing to integrate, we don't know how to integrate that yet. Ln squared, we know how to differentiate it, though, with the chain rule, but we don't know how to integrate it. So the move that we're going to try is natural log squared of x. We'll put the x squared over here with the dx. And then our integration column, we'll just use the power rule. Now the derivative side over here, we have to use the chain rule. So the derivative will be 2 natural log of x to the 1. So 2 comes down, leave the base alone, subtract 1. Then we have to differentiate the base. The derivative of that is a 1 over x, so we're going to have a division by x. And then we want a dx in here also. So there's our strategy. Let's see if it works. So we are going to have uv. So uv is the main diagonal, so let's write that like this. Usually we put the ln at the trailing end of a sequence of multiplication so that you don't mistakenly think something else is inside here, because most of us don't put parentheses around that. It's like just extra writing. So usually we stick ln at the end where it's obvious that something's not in it. You know, don't have to do that, but that's usually what we do. So uv minus the integral of v du. So let's see. So v du. So we're just going to multiply this stuff together here. So we're going to have 2 natural log of x divided by x multiplied by x cubed divided by 3. All right. And let's just keep coming across here, and a dx. Gotta have a dx. So then we'll simplify and hope for the best. So let's see. The inside we have a, well, I'll say this in a minute. I'm just going to write it first. So this is going to be 2x squared ln x all divided by 3 dx. So we canceled out a factor of x here. And many of us are inclined to pull that constant right out here, which you can do, that's right. It's equal for sure. But what we notice is that we are going to have to do integration by parts again. And it's a heck of a lot easier if you just leave a constant inside the integral if you're doing integration by parts. If you factor it out, then you have to have like monster brackets with the uv minus integral of v du inside. It's really easy to, it just gets messy. So with integration by parts, if there are constants in here, usually it's just easier to leave them in. You can just put them as part of the u, and it's going to work out just fine. So here's where we ask ourselves, is this integral easier than the original? Well, the original had a square and a square. This has a square and a first order. Right? Just a power of 1 on natural log. So it's getting better. The power on the natural log is going down. So that means we're moving in the right direction. So the way it would get worse, if this was x squared and natural log cubed, then it's getting worse. Or if it was x cubed and natural log squared, it's getting worse. So we need to see some distinct improvement. And that power went down. The most complicated factor is that natural log factor, and its power has gone down. So that's a good sign. So let's try it again. And when you're doing integration by parts more than once, so we call this repeated integration by parts, you want to stick with the same pattern that you did originally. So here we put the logs with the u. We want to stick with that and put the log with the u. If you all of a sudden switch them, you will just undo what you just did and you'll get back to where you started. So we don't want to do that. Now, the 2/3, you could put it with the u or the dv. It doesn't matter. You can put it in either one. This constant just has to be put in there somewhere. I've already written natural log here, so I'll just put it with the dv. It doesn't matter where the constant's going to go. But in general, it's going to be easier to leave the constant in this table than factoring it out and using monster brackets. So then we do our derivative column, 1 over x dx. Do our integration column. We'll get 2x cubed over 9. And we will have certainly that stuff. Okay, so then minus, and our integration by parts, our ultraviolet voodoo, is uv minus integral of v du. So we have uv minus integral of v du. There's a leading minus here. If there's a leading minus, it changes the look of this a little bit. We just have to remember to distribute that minus. That minus has to be shared across the whole uv minus integral of v du. So we're going to do our uv, right there, main diagonal. So we're going to get 2/9 x to the 3 times natural log of x. We can kind of start to see this pattern that the power on natural log started at 2, it's going down to 1, so this all looks good. So there's our uv minus the integral of v du, but because of that leading minus, it will end up being plus the integral of v du, so plus the integral of v du, so 2/9. Can you see that when we multiply v and du, we're going to end up with just an x squared? There's an x in the denominator and an x cubed in the numerator, so we'll cancel out one factor of x. Logs are gone. Great thing. Logs are gone. So now we have our final answer. Our final answer will be this. So that is the antiderivative. Okay, so notice the power of x here, this power of x squared. Down here we have a power of x, a square on the x. A lot of times if you have a factor that's a power of x, that indicates that you have to do repeated integration by parts. So this power of x had a 2 on it. The natural log was a big part of this, but we had a power of 2 here and we had to do 2 integration by parts. The same pattern is going to be here. We're going to have to do 2 integration by parts. It's not always going to be as simple as that, but often if you have a power of x, if you have x to the cubed, a lot of times it will mean you have to do 3. If you have power to the 4, you would have to do 4. Not always, but many times. So let's try this one. So you all tell me, what do you think we should pick for u? X squared is a great candidate. So we have 2 options. And let me point out one reason that this is really the only option. When you think about the exponential function, whether you put it in the derivative column or the integral column, you just end up with another exponential. The derivative of an exponential is an exponential. The integral of an exponential is an exponential. Like, it doesn't change the difficulty. It just stays the same. It's just cycling through. If you put the x squared in the integral column, it's going to get worse. It's going to become x cubed over 3. Whereas if you put the x squared in the derivative column, you get a 2x, so the power will go down. So in a case like this, where you have one function that's just going to sort of cycle around, and the other function has a choice to get simpler or get more complicated, you want to put it in the column where it's going to get simpler. So we're going to put the x squared here because it's going to get simpler when we differentiate it. And over here, we'll put the e to the 4x. It's just going to stay equally difficult when you integrate or differentiate, so we'll just put it there. And then the derivative is 2x dx. The integral here, the integral of an exponential is itself. And then RCR, divided by the exponent's derivative. And uv, so this is the product on the main diagonal, uv. We'll do the constant first, and then the power of x, and then the exponential. So there's uv. uv minus the integral of v du. So v times du. And so once again, we notice that things are getting better. The power on x is going down. So this is getting better. This looks better than it did originally. So let's do a little bit of simplification on the inside of this square, the inside of this integral. And again, let's not pull the constant out. So let's write this as 1/2 x e to the 4x. So that integral is looking better because the power on x dropped 1. So that's better. And then, once again, with our second integration by parts, we want to be consistent with what we choose for our u and our dv. So we chose the power of x last time. We want to do that again. And this time, I'm going to leave the 1/2 with the x. I could put the 1/2 with the e to the 4x. Doesn't matter. The constant can float between the derivative column and the integral column. Doesn't matter. And then here, du will be 1/2 dx. And then for dv, we're going to put the exponential function, e to the 4x times dx. And the integral will once again be e to the 4x over 4. All right, any issues with setting up that up to that point? So integration by parts is a technique that most people end up liking because it's very procedural. You know, you pick your U, you pick your dV. If it doesn't work, you just switch them. Like, it's not super heady. You just very procedural. Just got to grunt through it. So now we're in this situation again with this leading minus. So this minus is sitting in front of our ultraviolet voodoo. So we just have to make sure that we are careful with that, and that minus will have to attach to both. So we're going to have UV, main diagonal, so that upper left to bottom right. So it looks like 1/8, and there's a minus here, so it's minus 1/8 x e to the 4x. That's the main diagonal. Minus the integral of v du, but because of this leading minus right there, it becomes plus the integral of v du. And v du looks like e to the 4x over 8. dx. Let me leave that there for a second. All right, any issues with that setup there? That thing is an 8. And once again, we see the integral is easier than it was in the prior integral. So this integral is easier than that integral, which is easier than that integral. So we're in this progression of the integrals getting easier as we go through each iteration. So that comes down, that comes down. The integral of an exponential is itself divided by the derivative of the exponent. So what should the denominator be? 32. And we put in our constant of integration. So that'll be it. Integration by parts. Little voodoo. Little voodoo goes a long way. You are now integrating very crazy looking things. Inverse trig functions, natural log functions, products with powers. You're integrating complicated looking things. All right. You all try this one. So this one is an integration by parts that's definite, but that's okay. You know how to deal with a definite integral. Your main function, though, is this log function. So see if you can do integration by parts with that log function. And think about your definite integral. Give it a shot. I believe. Are you done? Do well on this one. Are you doing this right so fast? This derivative is not right.
Oh, no, I know. I miswrote it there, but that's right. Okay.
Oh, okay. And then
It's 2x. Right, exactly.
so the twos cancel,
Yeah.
so you end up with
Yeah.
this.
So I have it there.
So there, so those all cancel, that's x. So then you're plugging in e all the way across.
Mhm.
So
It's
it's
right here.
minus plug in a 1. Yeah, that looks fine.
Okay, so that's what you're simplifying. So it's 2.
Yeah, the only thing we could do is simplify that.
So you pull out.
Yeah, you have it's natural log of 2 times e. Is that what it looked like? So this you can turn into natural log. What is the rule? The rule says that natural log of a times b is natural log of a plus natural log of b. So we could turn this into natural log of 2 plus natural log of e. And natural log of e is going to be 1. Yeah. Log formulas. Anyone stuck on integration by parts part of it? Yes, the whole thing. That's right.
So a lot of times you will see them put a line here and put the one E right here. Where you
Oh, the one cancel, you're right. There's no way.
that derivative is wrong.
Because when you plug this one, which is 2.
Close. There's a little missing
No,
piece.
never mind. I can't. Yeah, because it's E times that. Yeah, so she can't.
Your derivative also has something
Natural
fishy in it.
No, because it's E.
So with that derivative, when you take the derivative of natural log of 2x, don't forget the chain rule. Do not forget the chain rule.
I guess you're right. Yeah, 'cause-
Yes.
Because what he said up there is the natural log of A times B is the same as natural log of A plus natural log of B.
All the way across. So for that UV part, that's
Yeah,
all.
so this is the, so this one should have come from here.
Yeah, that's right.
So you should have, this one is just
So,
from E
so
back
the way
here.
you have it now, this one should be.
So the derivative here, derivative of log is 1 over its inside.
You have
So 1 over 2.
Yeah, no, you're right. So you're missing an E.
Multiplied by the derivative of its inside. So
2 over 2. Yeah, that's an easy one to
That's loud.
easy one to forget.
Yeah, because ln of E is gonna be 1.
Find out, that's pretty darn good.
Parentheses, you're gonna have
But there's
ln
an
of E
excellent.
minus 1,
But we're now with the definite interval though,
which is 1 minus 1.
because we're gonna have these constants that will get plugged in,
Oh.
right? So those limits of integration are gonna get plugged in all across the board.
Wait, all of us?
Oh, yeah, you got your twos canceling. Good. All right, let's go through this. There's some fun little areas to get snagged on. With your choice, with your table here, there is no choice. You have to put the natural log of 2x with the u. And so common mistake here, you differentiate natural log. It's 1 over the inside times the derivative of the inside. So those 2's cancel, and you get 1 over x. And then integrating over here is no problem. V equals x. So we will end up with uv, so x natural log of 2x. And right here, typically with the notation, you'll put your evaluation symbol right there. So you're going to evaluate the uv with the same limits of integration as this upcoming integral. So then uv minus the integral, that will also be 1 to e. v du, well, we have an x times 1 over x, so we end up with just a dx here. And here you have a choice. You can evaluate this right now, or you can just wait to the end, because you're going to evaluate everything on the same interval anyway. So usually what I would do is just wait and do all the substitution at the very end. So now we're integrating, we found our antiderivative, and now we're going to use this integration interval across the whole thing. So you can do it in 2 steps, or you can just wait and do it all at once. So let's see if we can get through this. So plugging in the e, we're going to get e natural log of 2e minus e minus the antiderivative at 1. So minus, put in a 1 there, put in a 1 there, so that's minus natural log of 2. And then minus a minus is plus 1. So we'll have that. Okay, so then, if you wanted to just leave it like that, that's totally fine. Totally fine. There are some log rules that you could do. Like we know that the log of a product is the sum of logs, so you could break things apart. You could take that log of 2e and make it natural log of 2 plus natural log of e, and natural log of e is 1. You could go down that rabbit hole and do some log properties there. Totally fine, but this is sufficient here. If you wanted to do some extra log things, you would do e and then natural log of 2 plus natural log of e. So that's this product rule thing, back from college algebra. And then minus e minus natural log of 2 plus 1. You can't do anything there. natural log of e is 1. So this turns into a 1. And we will end up with some cancellation. We'll get e natural log of 2. But then e times 1 is e minus e. Those cancel. And then we have minus natural log of 2 plus 1. So you could go all the way down to there. That is where you'd have to stop, though. All right, let's try another one here. So you all set up the integration table. I want you to do the u and the du and the dv and the v, and then let's just spend 1 minute doing that. I want you to encounter that du and think about it carefully. Is the arctan going to go with the u or the dv? It's going to go with the u because we know how to differentiate it, but we don't know how to integrate it. So arctan is going to go with the u. And then think very carefully about the derivative. See this? Yeah, so I put it right up there. So 1 over 1 plus x squared is the generic formula. 1 over 1 plus x squared. So the y is not going to be with the u because then this will end up having to be a product rule if you differentiate, which is a mess. Yeah, with integration by parts, it's very rare that you're going to choose something that you're going to need the product rule to differentiate. Yeah, that's what I want to know. So what's your numerator then? What's the derivative of the inside? Okay, so that is the spot. So here is the spot where most people get a little bit tangled. Let's make sure that we understand it. So first off, we want the arctan with u because we can take its derivative. We don't want to put the y in there, though, because then it would be a product rule. We could differentiate that, but that's going to be a product rule, which is going to be a total nightmare. So we put the y over here. And notice that we're using a y, so what should the differential over there be? dy, yeah. And when we integrate here, we'll do this side first because this side's easy. So we get y squared over 2. Now the derivative of arctan is 1 over 1 plus x squared in general. So we know that du is going to be 1 over 1 plus, when we square this, we get y to the 4th. But then we have to use chain rule. We then have to differentiate the inside of that arctan, and that derivative is 2y. And then we have a dy. So right there, this is the spot. Be super careful right there. Chain rule. So we do our generic formula, but then we have to differentiate by the derivative of the inside. So y squared is inside. So then our uv will have 1/2 y squared inverse tangent y squared. And this, we go 0 to 1 over root 2. uv minus the integral of v to u. So minus integral v times du. Notice that there is a 2 in the numerator and a 2 in the denominator. So when we multiply these together, those 2's will cancel. And we'll end up with y to the 3 over 1 plus y to the 4 dy. And these limits are also 0 to 1 over root 2. So if you blew this derivative right here, if you blew that, then this integral is not going to be very integrable. Like the only reason this is going to be integrable is because we did the derivative properly. Like right now, what form is that in? Almost. Log, right? That's log-ish. All we have to do is multiply by 4 and 1/4. Now it's in log form. That just flicker. Okay. It's not just me. Please last for the semester. Please make it through. So looking at that, is there any piece of that you want to ask about? Yeah.
Why did you put the limits of integration from 0 to 1 over square root on the left? Yeah.
Because this antiderivative has to be evaluated here also. So these limits of integration apply to everything. So if we have a definite integral, the uv part also has to be evaluated on that interval, as does the v to u. So that's got to be evaluated across the board. And you can wait and just do it all at once, which is usually what I would do, because it just is easier to get into evaluation mode and do it all at once instead of doing some of it now and some of it later. So there, we'll just leave that part there. This, you all said that's in log form. So log form means natural log of the denominator, absolute value of the denominator. Bless you. And this is a definite integral, so this whole thing goes from 0 to 1 over the square root of 2. All right. Sometimes it's nice just to plug in the 0 first to see if it, gives you nothing. That's what we're hoping, that if you plug in 0, it gives you nothing. And it does. If we plug in 0 here, we're going to have 0. Arctan of 0 is 0, so that's all 0. Natural log of 1 plus 0 is natural log of 1, that's 0. So that's nice. Then we know we just have to focus on one limit of integration. It's not a pretty limit of integration, but let's see if it works out okay. So plugging in 1 over root 2. 1 over root 2 squared is 1/2. If we square that, we get 1/2. 1/2 times 1/2 is 1/4. So we're going to have 1/4 inverse tangent of, plug that again in here, we get 1/2. Keep going, we get minus 1/4 natural log. 1 over root 2 to the 4th. So that's going to be 1/2 times 1/2, which is 1/4. So we're going to have 1 plus 1/4, which is 5/4. So 1 over root 2 multiplied by itself 4 times is 1/4. And 1 plus 1/4 is 5/4. 1 and 1/4. So that is our final answer right there. Can you simplify inverse tangent of 1/2? Do we know an angle that has a tangent value of 1/2? And the answer is no. When we look at our 8-sector circle, the tangents are either 1 or minus 1, right? And if we look at the 12-sector circle, those slopes are either √3/3 or √3. No 1/2s. Sine or cosine, yeah, half comes up. But for tangent, inverse tangent of 1 we know, inverse tangent of -1, inverse tangent of √3, and inverse tangent of √3/3, but not inverse tangent of 1/2. Starting to like the inverse tangent function? Okay. You'll love, okay, look at this. So this is one of the coolest looking math equations ever. Now that some of you can appreciate arctangent, arctan 1 plus arctan 2 plus arctan 3 is pi. That's a pretty cool math formula. Arctan 1 plus arctan 2 plus arctan 3 is pi. You can prove that this is true with a little picture. There's this really cool math theorem book called Proof by Picture. It's got like 50 theorems and they're all proved with just little pictures. And this you can prove. Here is the proof. The proof that this is true is almost there. I just have to draw this properly. Let's see, I've got to draw a triangle in here properly. All right, I'm going to draw it. Where's the triangle? Okay, there it is. Now I see it. Right there. That's going down to that point, going to that point, and that's going to there. So this triangle here is going to be a right triangle. That is the proof. Okay, why? First off, pi is a straight angle, right? Pi is 180 degrees, straight angle. Inverse tangent of 1 is the angle that has a tangent of 1. If you look right here, this angle has a tangent of 1. These are squares. The tangent of this angle is 1/1. So that angle is arctan of 1. It has a tangent value of 1. This angle right here has a tangent value of 2. Arctan of 2 is the angle that has a tangent value of 2. This angle, tangent is opposite over adjacent. The angle opposite, or the side opposite, is 2 diagonals, and the adjacent is 1 diagonal, so the tangent of that is 2. Right? Tangent is opposite over adjacent. We have 2 diagonals over 1 diagonal, so its tangent value is 2. And then this angle is arctan of 3 because its tangent value is 3. 3 sides over 1 side. So that's a pretty cool picture that shows that that is true. Arctan 1 plus arctan 2 plus arctan 3 is pi. If you're going out and getting a tattoo this weekend, that's a candidate. Not bad. Right around the bicep, little, sort of. All right, maybe not. Maybe not. But it's a cool theorem, cool proof.
Dedication.
Dedication, right there. Okay, let's go ahead and do one of these applications. We are going to see shells and washers and discs ongoing. So we'll try to do a little bit of practice with each of them as we go on. So let's do this one, and then we'll take our break. So we have one bump of sine right there. Maybe that's not the right expression. One lobe of sine right there. And we want to revolve this around the y-axis. So here's our axis of rotation right there. We're going to go around this. And we want to find the volume of this solid. The natural choice here is to use a vertical element. So that'll be the vertical element at x. We don't want to use a horizontal element because then we're breaking sine into 2 parts based on the angle, which is not easy. So what technique? Is this going to be a shell, a washer, or a disk? Shell. Because we have parallel. Integration element and axis are parallel, so that's a shell. So we know the area of a shell, the area of a cylinder, 2 pi times the radius times the height. If we are wrapping ourselves around the y-axis, This distance right here, right there, that is the radius. Right? That element gets rotated around the y-axis. The distance that element is to the y-axis is the radius. And what is that? X. That's what x is measuring. X is measuring distance from y-axis. Height is the height of the element. And what's that being measured by? Sine x, the function. The function tells us the height. So that is the area of our cylinder. The area of the cylinder at x. And we know by now that to get the volume, we integrate the area. And when we look at this integrand here, we see a product. We see a product there. We're going to use integration by parts. So let's go ahead and set up our table, UDV. We have two choices. There's two functions here. There's an x and there's a sine x. So if we put the x with the dv, the power is going to get jacked up because we're integrating. If we put x right here, when we integrate, we'll get x squared over 2. That power is getting worse. So we're going to put the x over here with the u so that when we differentiate, the power goes down. And we'll put the sine over here with the dv so that when we integrate, it stays about the same, right? Sine and cosine are about the same. So integral of sine, derivative of both sides. And here is actually one of those things that I said I should follow through here. We've got a constant in front. And it's so tempting just to factor it out to the front. And we can do that. Let's do it this time. We just have to remember that we have big brackets. Big brackets. So this 2 pi has to be out in front with big brackets. And then inside we have uv, so minus x cosine x. uv. And our limits of integration have to apply here, so 0 to pi. Right, we were talking about that lobe of sine from 0 to pi, right there on the x-axis. uv minus the integral of v du. So v du is minus cosine x dx. So that goes in here. The minus can come out and make that a positive. Close the big brackets, put limits of integration. And that's where we're at. So let's keep trucking. I'm not going to evaluate yet. I find it easier just to wait to the very end. So you could evaluate this piece in front if you want right now. Let's just wait. Integral of cosine is sine. So then this whole quantity is being evaluated on the interval 0 to pi. And we're super psyched because if we plug in 0, we get nothing. If we plug in 0, 0 times cosine is 0, sine of 0 is 0, so we don't have to worry about that thing. Just focus on the pi. So plugging in pi, we're going to get minus pi times cosine of pi. Cosine of pi, negative 1. So we get that. And sine of pi, 0. So we're going to have that. So we're going to end up with 2 pi squared. That will be the volume of our solid.
Could you not have integrated that without doing the integration by parts?
No, because of this product. So if we have a product there, we could try u sub, but if we let u be sine, then there's no cosine for it to pick up. And if we let u be x, there's no sine of x that can get picked up by u sub. So with u sub, the derivative of u has to match somewhere in there. So if it was sine times cosine, we could use u sub, because the derivative of sine is cosine, and that could get picked up with the differential. But this, yeah, we're going to have to use integration by parts with that product. All right, let's take our break. Take 10. All right. So look at this horrible integrand. So this integrand, so we're going to call this integration by parts or ultraviolet voodoo with a twist. This you will not see in the textbook. They will not call it with a twist. But I think it's a very good way to refer to what's happening when we do the integration by parts. So when we set up our U and our dv, we've had some strategies to put one function or another function in the u position or the dv position. Here we have two functions. And the rub is that the exponential function, regardless of whether we put it in the derivative column or the integral column, it just becomes itself. If you differentiate or integrate an exponential, it's still itself. And sine, if you put it in the derivative column or the integral column, it basically does the same thing. It just wobbles back and forth between sine and cosine. So when we try to analyze what would cause the power to go down or make the integral simpler, nothing will. So watch what we're going to do. And so it's actually not going to matter what you put where. It will be the same amount of work either way. So look at the derivative. We end up with, so the derivative of an exponential is itself multiplied by the derivative of the exponent. Integral of sine is minus cosine.
Wait, why isn't there a 3?
Oh, there should be a 3. Thank you for pointing that out. Yeah, this angle is a 3x, so we should have a 3 in there. Thank you. And so when we integrate, what else has to happen there then? Divide by 3. Yeah, thank you. So there is our first integration by parts. And when we do this, I'm going to just give this integral a name. We can call it whatever we want. I'm just going to call it a name because we're going to have to do some algebra later. So we just pick our favorite letter, call it a letter, call it I. Most books will call it I. We're going to call it gamma, though, because gamma is cooler than I. So we'll just call it gamma. We like that better. That's a more interesting. No, that's not gamma. What's that? Omega. Yeah. Not ohm. We could use an ohm. That might be a cool symbol to use there. But that's an omega. You could use a gamma also. Anyone know what the big gamma looks like? Capital gamma? Capital gamma is this. If you wanted to use that. Hangman, right. I never thought of that. That's right. I was just watching someone play Hangman out there. Huh. Yeah, I could use Hangman. Okay, but we'll use omega. Let's use omega. So omega is just the value of this integral, right? We're just calling it something so we can refer to it. So gamma, omega, hangman, whatever. So whatever your favorite letter is. So let's do our UV. There's our UV. Minus the integral of v to u. So minus the integral of v to u. So I'm going to put a minus right here. And do you see that v du is going to be positive because of the two minuses? Right, there's a minus there and a minus there. So v du is positive. So when we do minus the integral of v du, it's just fine because minus and minus is positive. So we're going to have integral 2e to the minus 2x divided by 3. I'll put that divided by 3 right there. Cosine 3x dx. So uv minus integral of v du. Oliver?
What happened to the 2, like it's negative 2? Oh, never mind, no, I see it,
Okay, good. Good. Any other questions before we move on? When we look at this integral, it looks just as gnarly as the original. Doesn't look worse, doesn't look better though, right? We still have an exponential, we still have a trig function. Didn't get worse, didn't get better. We're going to persist. So we're going to keep going. We're going to let u be the same thing We're going to let u be the exponential. I'm going to group the 2/3 with that exponential. So I have 2/3 e to the minus 2x. And then we'll put the trig function with the dv. We're going to differentiate on the left and integrate on the right. So derivative here will be du equals minus 4/3 e to the minus 2x dx. Integral will be sine of 3x divided by 3. Okay. Stop me if you're not sure on where something's coming from.
How did we get the 4/3?
So chain rule. So the derivative of an exponential is itself. So we just rewrite itself, but then we have to multiply by the derivative of the exponent. Exponent's derivative is -2, so -2 times 2/3. Yeah. Left column is derivative column, so always remember the chain rule. Okay, so now we're in this scenario here. We're subtracting off uv minus v du. So then we're here. So if we're subtracting off, we have to remember to distribute that minus. So let's see. U times v. So that's going to be 2/9. Lots of fractions, huh? E to the minus 2x sine 3x. So there's uv. Minus the integral of v du. But really, because we distributed the minus, it's going to be plus the integral of v du. V du happens to be negative. That's fine. So minus integral 4/9 e to the minus 2x sine 3x. Okay, everyone okay with that?
Wait, why is it negative?
So we have this minus that's going to distribute. So it's going to be minus uv plus the integral of v du. V du is negative, so plus a negative is a negative. Plus times minus is minus. 3 negatives is a negative. So you can say there's 1, 2, 3 negatives. That's one way. It's not easy to keep it straight. Okay, but now what we notice is that we have like terms on the left and right. That's twisted. We've got on the left e to the negative 2x sine 3x. On the right we have e to the negative 2x sine 3x. So here is our strategy. So let's just leave everything alone for a second. All this is the same. This is minus 4/9 omega. Right? You agree? Because omega is that thing. The 4/9 is just a multiplier. So then what are we going to do? You do know. I think you know. What would you, so if I use the letter x instead of omega, what would you do? We're going to add it all to the left side, isolate the omega, divide by the coefficient. We're back into algebra 1. This is just a linear equation. Right? We have omega to the 1, we have omega to the 1, so it's just like x equals, 2 minus 5x. Right? So this is the twist part. We're going to twist this omega over to this omega and combine them. So what is 4/9 omega plus 9/9 omega? 13
Where did
nines?
that 9/9 come from?
1.
Oh.
Right, so anytime we want to add to, this has a fraction in front of it. It has a denominator of 9, so we're just going to make it 9/9 so that we can combine it more easily. Right, so we don't have to, but that's, I think, a pretty reasonable way. So we twist the omegas from the right over to the left. And then we still have all this stuff here. I'll write it out this time, because we're going to have to do some coefficient manipulation. Coefficient manipulation is coming. And here's a big thing you have to remember. We want to put a constant of integration there. Because we know that that omega is an indefinite integral. So the value in the end for an indefinite integral always has a constant of integration. And this omega here has a constant of integration built into it. But as soon as we add it to the left side, we sort of lose that constant of integration part of it. So we want to make sure that as soon as we move that to the left, that we put a constant of integration. Because we know every indefinite integral has a constant of integration. So what's the last step then? Multiply both sides by 9/13. So we'll divide by this or multiply by the reciprocal. We just have to isolate the omega. So that's it. So we're going to multiply by 9/13. So we're going to have 9 over 39. But it is funny, though, at this stage right here, where you're trying to figure out what to do next, it just looks way more complicated than Algebra 1 because you have exponentials and trig functions and omegas. But it's really just Algebra 1 where we're adding this like term to this like term. Everyone see that? So we're just going to add those two like terms together. And then we're multiplying by 9/13. There is our antiderivative. So this,
Can't you simplify the 9 over 39? 3 over 13.
yes, thank you. Great. Yeah, 3 over 13, right. Everyone know the division for 3s and 9s? If you add up the digits and the new number is divisible by 3 or 9 than the original was.
I just can't.
You all know that one?
Yes.
That used to be drilled into our heads. So if you have some number and you add up all the digits, if the new number is divisible by 3 or 9 than the original is. So if you have something like 39, definitely divisible by 3 because 12 is divisible by 3. If you just start adding stuff like that, that's divisible by 3 because if you add these all up, that number is divisible by 3. And the same is true for 9. So if the sum of the digits, so the sum of the digits here is 18. 18, add those together, you get 9. So that thing's definitely divisible by 9, also by 3. So add the digits. How many of you have never seen that? Wow, that's amazing to me. They're taking the fun stuff out of math. Right? Jeez. Okay, here is another integration of my parts with a twist. This one I took away all the coefficients. So you all do this one with no coefficients. There'll be a lot less algebra, a lot less arithmetic. So see if you can do this one. And that should take roll. Because this is school. Logan, Raquel is not here. Jack, Tim, Linda, Nick is not here. Patrick, Tabitha, Jesus, Anastasia, Connor, Hannah, Cameron, Ryan Rodriguez. Elijah, Brandon, Oliver, Skylar, Tyler, Tim, Daniel is not here, Ryan Tran is here, Peyton is here, Alyssa is here, Bradley is not here. sharp. So it does not matter what you put where. One strategy, if you're better at integrating trig functions, then you could put the trig function here where you're going to integrate it. If you're better at differentiating trig functions, you can put the trig function here. So if you're more likely to make a mistake when integrating, put it with the derivative or vice versa. Doesn't really, it's not going to matter where you put it. So I'll put it with the integral piece, put e to the x there. Did anyone do it the other way? Put the trig function with u? All right, let's see. Let's see if we come up with the same answer. So du is e to the x dx. And it is tempting when it doesn't matter which way to just sort of go in order. Put the e to the x first, cosine second. Doesn't matter. Okay, so there we go. And we're going to call this integral omega. So omega is going to equal uv minus the integral of v du. So uv, that's the main diagonal, minus the other diagonal, or minus the bottom row. So uv minus integral v du. And when you look at that integral there, yeah, it's about the same as the original. You have an exponential, you have a trig function. So we do it again. And the key here when we do it again is to be consistent. Let u be the exponential again. Let dv be the trig function again. If you do reverse them at this step, you're going to undo what you already did, and you're going to get back to the original question. So don't do that. du is e to the x dx. So this one is nice because it takes away all the constants that create fractions that make your life miserable. Fractions have a way of taking off the luster. All right, so u times v is negative, and we have this negative in front, so we have two negatives there, so that's going to be a positive. E to the x cosine of x. So there's uv minus the integral of v du. So minus the integral is going to be plus the integral of v du, and v du happens to be negative, no biggie. So we're going to get minus the integral of v du. Whoops, I want to put the e to the x in front. And that's where we notice that we have a like term. That is really just a constant times omega, right? Omega is e to the x, the integral of e to the x cosine x. So that's just an omega right there. So on the left we have 1 omega, and then we have this, and this is just omega. So we add the omega to both sides. And as soon as we add that omega to both sides, this is where we have to put in a plus c. Because we know this omega represents an indefinite integral. We know it has to have a constant of integration. So as soon as we combine the omegas, we make sure we put a plus c there. And then we isolate omega, so we divide by 2. And when we divide by 2, we divide everything by 2. And the constant divided by 2, you can just say that's still a constant. We think of the constant like a recycle bin. Add a constant to it, it's still a constant. Multiply a constant to it, it's still a constant. Just write it as a c. There is our answer. Integration by parts with a twist. All right, step there that you're not 100% on.
I'm still confused on like the omega part for the integral.
Mm-hmm. So we're going to let omega be the indefinite integral of e to the x times cosine x dx. So that's what omega is right there. Every time we see one of those, we can replace it with an omega. And so this is -1 times omega. You know, it's very similar to this one where we're going to let omega be the indefinite integral e to the negative 2x sine. Here's an e to the negative 2x sine, so we have this coefficient, but the indefinite integral part is just an omega. It's identical to what the original integral was. So we just need to call the original integral something because we're going to end up with a multiplier of it. And then we add them together and divide by the new coefficient. So this is a nice clean one here where we just have to divide by 2. We're not multiplying by 9/13 or something.
You've got the sign changes.
Mm-hmm.
The UV.
Mm-hmm. So when we have a minus in front of all this, then it really becomes that one. It becomes minus uv plus integral of v du. So when we do right here, we're going to, so that was this one. So now we're going to do that one here. So it's minus u times v is negative, so that's going to give us a positive. So it's minus uv, but uv is negative, so that's going to become positive right there. So we just have to count the minuses and see how many there are. So here's a minus right there. 1, 2, 3. So the integration by parts, the normal integration by parts is uv minus integral of v du. So there's 1 minus, and then there's 2 minuses, and then there's that minus right there. So that's going to leave us with a minus if we have 3 of them.
So when we took the integration by parts the first time, it originally had as a negative.
Yes.
And then when we did it again, we get a second negative.
Yes.
It normally turns positive.
Yes.
Because of the thing.
Is the thing being a minus when you multiply? Yes.
Okay,
Exactly.
pull the negative out.
Yeah. I mean, you just have to sort of do whatever works for you. So here we know that it's going to be minus multiplied by uv, so it's going to be negative uv. And then we look at uv, and uv is negative, so negative uv becomes positive. Everyone following that? So we've got that minus multiplied by that minus gives a positive. This is the one that tends to throw people off right there, because you have this minus out in front. So it really puts us in this scenario where we do plus the integral of v du. And so then whatever the sign of v du is, that's what's going to stay. And if it's plus the integral of v du, whatever the sign on v du is, that's what's got to stay.
Everything,
That's the one that's got the 3 minuses.
everything we integrate by parts, we change the sign.
If there's minuses.
Yeah, so just counting the number of times we use integration by parts, then we can track how many.
Yeah, it's a combination of that plus the number of minuses, because sometimes
Plus
this
the number of times.
minuses that are in there. You could have 2 minuses on the diagonal. Cameron?
So the e to the x sine of x comes from the top table, but then everything after, like the e to the x cosine of x minus, that comes from voodoo or whatever.
Yep, the
From
voodoo.
that one, right?
Yeah. That's right.
Alright.
That is correct. All right, let's go to a new topic, since we are now masters of integration by parts. All right. So here we're going to integrate powers of trig functions. And we're going to break it into 2 groups of powers. We're going to have sines and cosines paired off, and then we're going to have secants and tangents paired off. So powers of products of trig functions. Powers of products. And we're going to come up with strategies based on the exponent and what the exponent's parity is, whether it's odd or even. In the easiest case, is if one of the powers is odd. So if we have sines and cosines multiplied together, if one of the powers is odd, that's the simplest case. We already know that if we have sine squared or cosine squared, we power reduce. We already know that. But if we have an odd power, if we have a pile of sines, a pile of cosines, and one of them has an odd power, simplest case. We pull one off, so split off one factor for the differential, and then convert the leftovers. And when we say convert, if we have sines, we convert to cosines. If we have cosines, we convert to sines. When we're dealing with secants and tangents, if we have secants, we convert them to tangents. If we have tangents, we convert them to secants. So secant tan, sine and cosine paired off together. So here we see, oh, okay, there's an odd power. So we're going to pull one off and put it with the differential. So if we have an odd power, pull one off and feed it to the differential. Put it over there. And now these are what I'm referring to as the leftovers. These are left behind. These are leftovers. So we started with sine cubed. We pull one off. Now we have 2 left over. We need to convert those to its co-function. So we need to convert it to cosines. So sine squared is 1 minus cosine squared. And now we're ready for u sub. What would we let u be? Cosine. So whatever we put with the differential over here, we want to let u be its companion function. If we let u be cosine, its derivative is going to line up with this. So we're going to do this in different ways. If we had the odd power on cosine and we pulled the cosine off, then we're going to convert everything over here would be sines. So we're going to let u be sine, and its derivative would line up with the cosine in the differential. Okay, so if we let u be cosine, then du is negative sine of theta d theta. And if you need to isolate the sine of theta, a lot of people just skip this third step. You can do it in your head easily. Doesn't matter. And I should have used an x because we're dealing with an x here. So x, make those x's. So the integral is going to turn into something pretty easy looking. So we're going to end up with minus out in front, 1 minus u squared du. So that's almost always the case with these, that you end up with just with a simple power on your u. This integrates. The integral of 1 is u. The integral of u cubed is u3, u to the 3 over 3, plus c. And then we back substitute and distribute the minus. And that's our strategy. So odd power is going to be the simplest. It's going to unravel very nicely like this. So odd powers, pull one off, convert the leftovers. Let u be whatever you didn't pull off. Right? So you pull off, you're going to let u be the other function. So here's one. We've got powers of sines and cosines. We see that cosine has an odd power, so we're psyched because that's the easiest scenario. So the rule says if we have an odd power, pull one off. So we're going to be left with cosine to the 4th. Those are our leftovers. We're pulling off one cosine and grouping it with the differential. So what are we going to let u be? Just sine. So u is going to be either just sine or just cosine because the power will then be u to the... So remember, if you let u be sine squared, then the derivative would be 2 sine times cosine. It would get really messy. So your u is always just going to be sine or just going to be cosine. So here we pulled off a cosine, so we know we're going to let u be sine in the end because the derivative of sine will then be cosine. Okay, but now we have to convert the leftovers. So we pull off one, now we convert the leftovers. And converting leftovers, Pythagorean theorem. We always use the Pythagorean theorem to convert. So cosine squared is 1 minus sine squared. But then because of the 4, we have to put a 2 there. Because we have cosine squared times cosine squared. So that's 1 minus sine squared times 1 minus sine squared, which is that. So now we're ready to roll with our u sub. We're going to let u be sine of x, which tells us that du is going to be cosine of x dx. So if u is sine of x, we have to replace all those signs with a u, and we're going to end up with a polynomial. We're going to end up with just a bunch of powers of u, which we can integrate using the rule, the power rule. So here we have a little bit of algebra. We have to FOIL, so we're going to get u to the 4th minus 2u squared plus 1. Foiling. And then we have to distribute the u squared. And we'll end up with something, you'll end up with stuff like this very frequently, just these powers of u. So we'll integrate each of these. And then what's our last step? So back substitute, get back to sign. Whenever we let u be, so here we let u be sine x. So we're going to just plug that back in. And we've got our antiderivative. Yeah.
I'm just confused on how you converted the cosine to 1 minus u squared, or the 1 minus sine squared.
1 minus sine squared squared.
I get the equation for that, so sine squared plus x cosine squared equals 1, right?
Mm-hmm.
But I don't know.
Gotcha. Yeah, I think I know what you're asking. So you're okay with that?
Yes.
So think about cosine to the 4th. Think about that as cosine squared all squared.
Okay.
So then we're going to take that cosine squared that's down here in the base, and we're going to replace it with that. But then that is in turn squared.
Okay.
So you can think of it that way, or you could also say that cosine to the 4th is cosine squared times cosine squared. And so then you're going to replace each one of these with 1 minus sine squared. So you get 1 minus sine squared quantity squared,
Okay.
which will then force us to FOIL. That make sense? Good? Good, good? All right. Tans and secants then. So, and let me just say that if you had both even powers, so if you had sine squared and cosine squared, you have to power reduce both of them. So if things are all even with sines and cosines, you've got to use power reduction. So you're really hoping that there's an odd power. Okay, tangents and secants are very similar. We have to be strategic, and let's just put some derivatives up here because it's helpful to remember. So the derivative of tangent is secant squared, and the derivative of secant is secant times tangent. Okay. So, if secant has an even power, we're going to pull off secant squared and convert the leftovers. So if secant has an even power, we're going to pull off secant squared. So right here, secant has an even power. Now, there's not a lot of secants. There's only a secant squared here. But I'm just going to conceptually think of it as moving it over and tying it with the differential. So I'm going to stick it over there. If there was a secant to the fourth, we would have leftovers and we would want to convert them to tangents. But here we're just going to focus on the concept. If we pull off secant squared, what do we want to let u equal? Tangent, because its derivative will then pick up that secant squared that we put with the differential. Right? So then here we're going to say, all right, let's let u be tangent. And its derivative is secant squared. So there's the du. So if there were other secants over here, if secant had an even power, if it was secant to the 6, we would pull 2 off, and then we'd have to convert that secant to the 4th. And the goal would be to let u be tangent, because that secant squared that we pulled off will have, well, that'll be the derivative of tangent. So that's going to be our strategy. So this one is going to be pretty straightforward, because we're just going to end up with u squared du. And then that's going to be u cubed over 3, so 1/3 u cubed. And then all we have to do is back substitute. We take the u, turn it into a tangent. So we're going to have a 1/3 times tangent cubed of x. So if secant is to an even power, and so you want to have these derivatives kind of really, really well solidly placed in your head. If secant's even, you're pulling off secant squared, because if you let u be tangent, its derivative will grab that secant squared. Now, if the tangent power is odd, we're going to pull off a sectan and convert the leftovers. So if tangent is odd, we pull off a sectan, with the goal being that we're going to let u be secant, because then the derivative of secant will pick up the sectan. So if tangent is odd, we're going to pull off a sectan. So if tangent is odd, and we pull off a sectan, what's the power on tangent that's left? Even. If the power on tangent is odd, and we pull off a sectangent, we're pulling off one tangent from an odd power of tangent, then we're going to be left with even number of tangents, which are convertible with the Pythagorean theorem. The Pythagorean theorem can convert even powers. It can't convert odd powers. It can convert even powers. So if tangent has an odd power, we're pulling off a sectan. That's going to go over to the differential with the foresight that, oh, well, then we need to have just secants over here. So if we let u be secant. So we'd have to have an even number of tangents so that we could turn them into secants with the Pythagorean. So let's see. So there's an odd power on tangent. So odd power on tangent, it says pull off a sectan. What do we do when we're trying to, when something is not there in math? We multiply by 1, right? We just make it. Use our magic wand. We make it. So if there's not a secant and you're supposed to be pulling off a secant, just put one in. And if you put one in the top, you also have to put one in the bottom. So we're just going to make it, right? We're going to cook it up. So then we are looking at our odd power of tangent. We know that we're going to pull off a secant times tangent for the differential. So that is our hypothetical du. So we know that we're going to have just secants left. So we want just secants so that we can let u be secant and then du would be sectan. So let's see what's left over here. So we're left with tangent squared in the numerator. Well, let's just do it one step at a time. So we're left with that. Now we can convert the leftovers. So these are what we're referring to as leftovers. So whatever went to the differential, whatever you took it from, is left over, and then you convert it to the companion function there. So in this case, convert to secants. So tangent squared is secant squared minus 1. Or secant. And then our differential. So here's a really good time to, I mentioned this, I think I mentioned this. So remembering the tangent and the secant identity, I really recommend this picture. This really helps. So this triangle right here, this is a unit circle, so that's a 1. This vertical side is tangent, and this hypotenuse is secant. And this is the angle theta there. That triangle is a very, very good visual representation of tangent and secant that helps to memorize the identity. So as this angle rotates counterclockwise, you can see the tangent just gets taller and taller, it gets bigger and bigger, as does secant. But then at pi over 2, there's no triangle there, which means it's undefined. So at theta equals pi over 2, both tangent and secant are undefined, right? Because both of them have cosine in the denominator, and if cosine is equal to 0, division by 0. So that triangle gives you a really good relationship between the two. You can see that secant's always bigger than tangent, because secant's always the hypotenuse, tangent's always that vertical side. And you can see that at 45 degrees, tangent's going to have a height of 1, which we already know. So if we're at 45 degrees, we're right there. So that would be a 1. This is tangent of theta. That's secant of theta. So at 45 degrees, pi over 4, value of tangent is 1. And what's the value of secant? This triangle is 1 here and 1 here. What's the hypotenuse? Root 2. Right, so secant of pi over 4 is going to be root 2. So that's a good one to have just to memorize this identity, because you need to be able to manipulate it back and forth. And you can see it better here. Secant squared is equal to tan squared plus 1, or tan squared is secant squared minus 1. You can just see it better if you have that visual. Then we're going to go to u sub. So we're going to let u be secant. And du will be secant tangent. Great. Because now it's set up perfectly for that. So our substitution is going to yield integral of u squared minus 1 over u du. Now this fraction is improper. So you might say, oh crap, we have to do long division. But we don't here, because we can split the fraction, and when we split the fraction, we end up with two things that are integrable. I mean, that is actually the long division if you were going to do it. That's what it would give you. But in this case, we can split the fraction. It's going to be the same outcome as if we did do long division. That's easily integrable. We know that the integral of u is u squared over 2. And what's the integral of 1 over u? Natural log absolute u. So that's going to be our antiderivative with u. And then we just have to go back. We want to get all the way back to secant of x. So we'll have half secant squared minus the natural log of the absolute value of secant plus c. Any step there? Good. All right, let's take a look at another one. Okay. So with this one, we have odd on tangent. So we could pull off a secant tangent and convert the leftovers. If we did that, we would have tangent to the 8th that we would have to convert back over to secants. Tangent's odd. If we pull off a sec tan, we'll be left with tan to the 8th to convert. Secant is to an even. So we pull off a secant squared, and we're left with the secant squared as the leftover. We'd have to convert the secant squared to tangents. That's going to be a lot easier to convert secant squared over to tangents than tangent to the 8th over to secants. So if both are candidates, of course both will work, but in this case, one is going to be a lot easier than the other. So if we have tangent to an odd, we're only pulling off one tangent, so we're left with tan to the 8th. Right? But if we have secant to an even, and we're pulling off 2, we're only left with 2, that's an easier conversion. So that's what we're going to do. We'll approach it that way. Definitely you could do it the other way. Does not matter. So we're pulling off a secant squared, leaving a secant squared. So this secant squared is going to be paired off with the differential. So we're grouping it over there. So that's our perspective du. Right, we're going to let u be tangent, because the derivative of tangent is then secant squared. That's going to get picked up with the derivative of tan. So these are the leftovers, and those need to be converted. They're converted with the Pythagorean theorem. So if I think about that triangle visually, secant's the hypotenuse. Secant squared is going to be tan squared plus 1. So we're going to have tan to the 9th, and then tan squared plus 1. And then the secant squared. And now we come over here, we say, let's let u be tangent. So du will be secant squared theta d theta. And then it's just going to turn into a pretty reasonable integral. We're going to have u to the 9, u to the 2 plus 1, and du. Distribute that u to the 9th, and then integrate. So we'll get u to the 12 over 12 plus u to the 10 over 10 plus c. Back substitute. Done. Not too crazy. Not too crazy. But we do need to remember what to do in each of these scenarios. So as a general kind of plan making sense, whatever you pull off, that's your target du. So you want to let u be whatever has that as its derivative. So if we pull off a secant squared, we want to let u be tangent so that the derivative of tangent will pick this up. And that means all of this should turn into tangents. We have to have just tangents if we're going to let u be tangent. So this one, that is not considered an even power on secant. When we say an even power on secant or an odd power on tangent, we mean in the numerator. All right, so this is not going to be considered an even power on secant. That secant's in the denominator. So we're talking about powers that are even or odd. They're up in the numerator. So this one definitely only has one way to do it, and that is to focus on the power of tangent being odd. So power of tangent odd, we pull off a sec tan. But again, there's no secant there to pull off, so we're going to be creative again. So we have tangent cubed of theta. Let's put this secant squared down below. And we're supposed to pull off a sectan when tan is odd. All right, there is no sectan to pull off, so we create. We create a sectan by multiplying up and down by secant. Now we can pull off a sectan. And what are we left with? We're left with a tangent squared in the numerator. Denominator is secant cubed. And then we have a secant tangent that's going to hang out over here and is our perspective du. So that's all together. So our goal then is to let u be secant, because the derivative of secant will pick that up. These tangents right here, these are leftovers. We need to convert those. Those are leftovers. So our focus was on odd power of tangent. We pulled off of one tangent, and we left two behind. We need to convert those. So again, if we have a good visual of that triangle, tangent squared is secant squared minus 1. Okay, u, ready for u. U is going to be secant. And then du will be secant theta, tangent theta, d theta. And that's going to clean this up so nicely. Well, let's see if I'm telling the truth. So we plug that in. So we're going to have u squared minus 1 over u cubed du. Whoa, what is our strategy that we're going to use here? Split the fraction. So this splitting fraction thing is, notice that it's viable because the denominator is a single term. Then you can distribute it into the numerator. When we get to trigonometric substitution, that's going to be a big deal. Our denominator will often be two terms, and our goal is to make it one term so that we could then split fractions or do other things. So here it's already one term, so it's very easy. If this fraction was flipped over, it's way harder. When the denominator has two terms, it's much more difficult. So we usually are aiming to make the denominator one term, because then we can do things like split the fraction. So we have that. Integral of 1/n. Natural log. Absolute value of u. So here we're going to add 1 to the exponent and get -2. Divide by -2. That's going to give us a plus 1/2 out in front. Let's see. Back substitute. So we let u be secant. So we're going to convert all these u's over to secants. So we're going to have natural log of absolute secant. And it was a theta or an x? Theta. Plus 1/2. 1 over secant squared. And what is 1 over secant squared? Cosine squared. Right? If we have 1 over secant, that's the same as a cosine. So if we have 1 over secant squared, that's the same as cosine squared. Does that make sense? So this we could write as cosine squared of theta plus c. 1 over secant is cosine. So 1 over secant squared is cosine squared.
What did
Is it generally a good idea to do this method with the lowest power?
Yes,
Like we could have,
if you had a choice.
if you have a choice,
Yeah.
you usually want to take the lowest.
If you have a choice, then usually, yeah, if you have a choice, then always pick the lowest power. Yeah. I mean, the problem is you've got to, yeah, not always going to be 2 choices. Right?
I know the converting the leftovers.
Yes.
So for the tangent and secant, X saw that if you're converting secant to tangent, it's tangent squared plus 1.
Right.
For tangent. So is it always going to be like that? Or is
Yes.
there-
So if we have tangent squared, that will turn into secant squared minus 1. If we have secant squared, that will turn into tan squared plus 1. Yeah, always. Always. All right, let's just see where we're at. There is a bazillion reduction formulas. You do not need to know these reduction formulas. The only ones you need to know, sine squared and cosine squared. Those are the only 2. If you look, it depends on how big a web page you look at. Some integration tables, there's like 20. Some there's like 30. Some there's like 50. There's a bazillion integration formulas that you can use. This is not math. This is just, matching the n with whatever number it is. This is like something else. This is pattern recognition. So this is not something you'll be tested on, but in the homework, you should be able to look at this and just do it. You should be able to look at that right there and say, okay, n is 5 in this case. Let's go through it. So I'm not going to test you on this, but on the homework, you'll see some of these things. So we would look here, n is 5, so this is going to turn into secant cubed x tangent x. N minus 1 is 4, because the n starts as 5. And then we come over here, and we're doing n minus 2 over n minus 1, so it's 5 minus 2 over 5 minus 1. So that's going to be 5 minus 2 is 3, 5 minus 1 is 4. So we're just doing this kind of thing, where we're just following a recipe for how to integrate. And now we still have an odd power on secant here. So we're just going to do it again. So we have a 3/4 secant to the 3, odd power right there. We're just going to plug it in, so that's going to give us a secant tangent of x. So secant tangent x divided by what? 2? N is now 3. 3 minus 1. Plus, so we're plugging in a 3 right there, so 1 over 2, so plus 1/2. Integral secant to the 1 of x dx. Close the parentheses. So we're just sort of going all the way down. Bless you. And the last step will be to integrate secant, which we'll do on Tuesday. Integrate secant on Tuesday. So these, again, you don't need to know those, but there'll be a couple in the homework. If I wanted you to do one on a test, I would give you the formula. All right, let's stop there. Let's go look at the sunshine. All right, isn't it nice out now?